length can combine with the other unit of varying length in the final termination step. So this is a random process. So to express chain length, it is generally expressed in terms of molecular weight of polymer chain related to relative molecular mass of the monomers and the number of monomers connected in the chain. That is how many monomers have united together to form that polymeric chain. In other words, polymer is a complex mixture of molecules of different molecular weights. Based on this, polymers may be categorized as polydisperse and heterogeneous in composition, monodisperse and homogeneous in composition. Now let's discuss this meaning of the words polydispersity and monodispersity in context of polymers. What are monodisperse polymers? In case of monodisperse polymers, they are uniform in which all molecules have the same degree of polymerization or relative molecular mass. That is, the degree of polymerization of all the molecules is uniform. All the natural polymers, especially biopolymers, proteins, they are monodisperse in nature. As we can see from this image, all the molecules, that is, all the components constituting or forming this polymer sample have same degree of polymerization or they have same relative molecular mass. Now we can take up this example of monodisperse polymer like 344 units of the same 15 carbon long chains unite together to form a polymer sample. So this is the example of monodisperse polymer. While in the case of polydisperse polymers, non-uniformity exists. That is, polymer chains of unequal length are there and the molecular weight cannot have a single value. It exists as a distribution of varying chain lengths. In the upcoming slides, we'll be discussing in detail that what do we mean by a molecular weight distribution, how do we express it. So we will discuss in the upcoming slides the distribution of molecular weights. As we can see from this image, that there is non-uniformity in the chain lengths of this polymer sample. That is, they have the unequal length and in the polymer sample, the molecular weight is unequally distributed. So we call it as polydisperse polymer. If we consider the example, like we have 4 units, 15 carbon long, 13 carbon long, 11 carbon long, 10 carbon long, and the units that come together to form the polymer sample, 109 units of 15 carbon long, 98 units of 13 carbon long, 82 units of 11 carbon long, 74 units of 10 carbon long. So there is heterogeneity in the composition. Like chains of different length, varying length have contributed towards the formation of a polydisperse polymer, whereas in this case, all the units were of the same chain length and there were 344 units contributing towards the monodisperse polymer. Hence, what can we conclude? We can conclude that the molecular weight is expressed in terms of average of the molecular weights contributed by all the individual molecules present in the sample. We cannot have a specific number. We cannot have a single value. What we can say instead, polymer molecular weight is defined as a distribution rather than a specific number. And this I've already made clear from this example. So we'll express the molecular weight of polymer in terms of averages and not a specific number. Now, before I proceed further to how do we express the molecular weight of polymers, you have done it in your junior classes also. You are familiar with the terminology, that is number average molecular weight and weight average molecular weight. But before that, I would like to discuss with you what do we mean by molar mass distribution or molecular weight distribution? The molar mass distribution or molecular weight distribution simply describes the relationship between number of moles of each polymer species and molar mass of that species. Species, I refer to a particular species that contributes towards the formation of the total polymer sample and the molar mass of that species. Molecular weight distribution, I've abbreviated as MWD, is basically, or it refers to amounts of component polymers that make up a polymer, that make up a final total polymer. Component polymers, it refers to a convenient term that simply establishes the fact that all the polymeric materials comprise a mixture of different polymers of different molecular weights. That is, a total polymer sample is a mixture of different polymers that have varying molecular weights, that have variable molecular weights. The ratio of weight average molecular weight to the number average molecular weight gives an indication of MWD. I will discuss in the upcoming slides what do we mean by weight average molecular weight and what do we mean by number average molecular weight. So, molecular weight of a polymer is expressed in two ways. Number average molecular weight, that is Mn bar, and weight average molecular weight, that is MW bar. So let's first discuss what do we mean by number average molecular weight of polymers denoted by Mn bar. This refers to if in a sample there are N1, N2 and N3 number of molecules having respective molecular masses M1, M2 and M3, then the number average molecular weight is given as the product of number of molecules of each type multiplied by the molecular mass of that type of molecules and adding on to it another type of molecules, that is N2, multiplied by the respective molecular mass, and so on. If there are so many components, we will take that number of components in the numerator and we'll divide by the total number of molecules, that is N1 plus N2 plus N3 and so on. This product N1 into M1 denotes the contribution, molar mass contribution of a particular type of molecules towards the total polymer sample's mass. And if we take total of this, that we summate it, taking summation of it gives us the total mass of the polymer divided by the total number of molecules present in the sample. It is nothing else but the simple that we use to take average of anything. Here N1, N2 and N3, they denote the number of molecules, while M1, M2 and M3 denotes the molecular weights. So the average is simply given by total mass of the polymer sample divided by the total number of molecules present in the sample. Now next, coming to, before we come to weight average molecular weights, let's take up an example to understand number average molecular weight. For example, you have a polymer sample. This is a clear example of a polydisperse polymer sample, as I discussed. As you can see, this polymer sample is composed of variable chain length, and the molecular weight of this chain length is obviously different. 109 units of chains having molecular weight 212.25 are combining with 98 units of molecular weight having 184.22, then 82 units having molecular weight 156.19, then 74 units having molecular weight 142.29. Now, if we need to evaluate the number average molecular weight, what do? We simply calculate the contribution by 1 unit as we did in the formula in the previous slide. That is 109 number of molecules multiplied by its molar mass, then 98 multiplied by its molar mass, 82 multiplied by its molar mass, 74 multiplied by its molar mass divided by the total number of molecules. So number average molecular weight can be measured on the basis of colligative properties. You are well familiar with what do we mean by colligative properties. You have been introduced with colligative properties in your junior classes. These are the properties that are wholly solely concerned with the number of solute particles, irrespective of the nature of the particles. So these can be measured on the basis of colligative properties like lowering of vapor pressure, depression in freezing point, etc. Coming to weight average molecular weight of polymers, that is represented as MW bar. In this, if M1, M2 and M3, that is small M1, M2 and M3, why do I specify small? Because with capital M1, M2, we would be specifying its molecular masses. So if M1, M2 and M3 are the weights of species with molecular masses M1, M2 and M3, then the weight average molecular weight is given as MW bar is equal to M1 into M1, that is weight of that particular species multiplied by its molecular mass, weight of the species 2 multiplied by its molecular mass, and so on, and divided by the total weight of the species and not the total number. I would like to mention that in what do we did in number average, we considered the number of molecules instead of weights of the species. And here we took N1 into M1. Here we are multiplying M1 into M1. Similarly, if I take summation of all, so MW bar is represented summation of Mi into Mi divided by summation of Mi, that is the total mass. But as we have seen in the previous slides that Mi is equal to number of molecules of that type into molar mass. So what Ni represents the number of molecules of mass Mi. So finally, we conclude with the formula MW bar is equal to N1 M1 square, because we have put this M1 as N1 into M1 and this M2 as N2 into M2. Finally, what do we get? N1 M1 square plus N2 M2 square plus N3 M3 square and so on. So this is what we call as weight average molecular weight of polymers. This weight average molecular weight can be measured by light scattering experiments, viscosity measurements, etc. Now, a very important parameter that needs to be discussed here is that weight average molecular weight is higher than number average molecular weight in polymers. This is a very important question also that you can get in your exams, that weight average molecular weight is higher than number average molecular weight in polymers. Why is it so? Now, as I have already discussed with you the difference between number average molecular weight and weight average molecular weight. Now, compared to Mn bar, MW bar takes into account the molecular weight of a chain in determining contributions to the molecular weight average, rather than considering the number of molecules. Obviously, if the chain is more massive, the contribution towards MW bar will be more. Mn bar, the average molecular weight, it is evaluated from the mole fraction distribution of different sized molecules, that how many molecules of a particular sized molecules are present and how many molecules of a different sized molecules are present. That is, we are concerned with the number of molecules. While in MW bar, the weight average molecular weight is calculated from rate fraction distribution. That is, how much are they contributing weight wise. Since larger molecules in a sample weigh more than smaller molecules, the weight average has higher values and is always greater than Mn bar. This graph represents, on y-axis we have number of molecules and on x-axis we have molecular weight, and in the distribution you can see that weight average molecular weight is higher than the number average molecular weight. Now we need to know what do we mean by polydispersity index. Now we are in position to define What do we mean by polydispersity index? Polydispersity index calculated for a particular polymer is the weight average molecular weight divided by the number average molecular weight. That is the ratio MW bar and MN bar. The polydispersity index or this heterogeneity index. Why do we call it as heterogeneity index? Because we are talking of a polydispersed polymer. We are talking of the heterogeneous composition where different chain lengths of varying molecular mass were contributing. This is a measure of distribution of molecular mass in a given polymer sample. What does this indicate? It simply indicates the distribution of individual molecular masses in a batch of polymers. As I showed you the image of how the variable, how in a polydispersed polymer, the different molecular masses are contributed by various molecules. The PDI has a value equal to or greater than 1. Greater than 1 because I mentioned MW bar is greater than MN bar. But as the polymer chains approach uniform chain length, or we can say as the weight dispersion of the sample narrows, that is, as our sample proceeds from polydispersity towards monodispersity. So MW approaches Mn bar, and in that unlikely case, all the polymer molecules will have identical weights. That is, we will now have a pure monodisperse sample, as I showed you in the previous slides. In that case, the ratio PDI becomes unity. So next, we are now in position to discuss mechanical properties of polymers. For the practical applications of polymer, it is of great relevance to be familiar with some of its basic mechanical properties. Like, for example, if we want to use some polymer for a certain application, then it is very important that we should have certain basic information about that polymer. The basic information composed of how much it can be stretched, how much it can be bent, how hard or soft it is, how it behaves on the application of repeated load, how much load it can bear, or what is the threshold molecular weight, and so on. What do we mean by threshold molecular weight? I'll be discussing with you in the upcoming slide. Now, the properties of a polymer, certain mechanical properties of a polymer like tensile strength, impact resistance, resistance to cracking, and melt flow viscosity, they're directly related to molecular weight and molecular weight distribution of a polymer. I will be discussing these properties with you. No doubt we will not be going into so much of detail, but we will be discussing how these properties are affected by DOP, that is degree of polymerization. DOP has direct impact on these properties, whereas properties like density, refractive index, solubility, they are independent of the molecular weight. Now, before we discuss the mechanical properties, let us discuss what do we mean by threshold molecular weight. This is a very important definition for you people. Threshold molecular weight is the minimum molecular weight that a polymer must attain to develop the properties needed for a certain application. That is, if we want to implement or if we want to use a particular polymer for a certain application, it has to attain a minimum molecular weight so that it is fit for that particular application. Now, the knowledge of it being important because we need to stop our polymerization process or we need to control our polymerization process at that stage, depending upon what application do we require. So this is known as threshold molecular weight. For example, low molecular weight polymers, they are brittle and possess less mechanical strength. While high molecular weight polymers, they are tough and non-flexible. They cannot be easily handled. So their variable molecular weight leads to variable applications. And though we have already discussed what do we mean by degree of polymerization, just to have a recall, because I need to discuss this term again in the mechanical properties, let's have a look on this definition again. The number of repeating units in a polymeric chain is called degree of polymerization. In other words, Degree of polymerization is a number that indicates how many repetitive units or monomers have come together to form that particular polymer. And this is represented as small n. In the previous lecture of the series, I had already explained this DOP, taking the example of polyethylene also. Now let's take up mechanical properties of polymers. In the mechanical properties of polymers, firstly, I'll be discussing with you what do we mean by tensile strength of a polymer. Before we actually come to tensile strength of a polymer, let's see what is strength, simple strength of a polymer. When we talk in a layman language, that is, what do we mean by strength of a polymer? It refers to stress, that is force applied divided by the cross-sectional area of the material. That is, this is the surface property, area property of the polymer. That is stress necessary to break the sample. Strength of a polymer refers to stress necessary to break the sample, and it refers to force. The various types of strength in context of polymers are tensile, when we discuss the stretching of the polymer; compressional, when we discuss compressing the polymer; flexurial, bending of the polymer; torsional, twisting of the polymer; impact, hammering, and so on. But here we'll be discussing a little bit of variation of tensile strength. Tensile strength is a measure of the stress needed to break a material by stretching. That is, how much a material should be stretched so that it breaks. Tensile strength is important for a material that is going to be stretched or under tension. We should have a prior knowledge of the tensile strength of a material, because if we need to stretch a material, is to be very important to know that how much highest load we have to apply so that the material snaps into two. The tensile strength is the highest load applied before it snaps into two. Or we can say tensile strength is material's ability to resist tearing, that how far it can bear that load till it tears off. An example of tensile strength is how much force can be put on a material before it tears apart. So this is what do we mean by tensile strength of a polymer. Coming to impact resistance. Impact resistance is generally mistaken as impact strength, while it is not about strength at all. Strength refers to a force, while impact resistance is an energy. It is the energy required to break the sample into two or more pieces. When we discuss strength, it was force. So this is the energy required to break the sample into two or more pieces. In other words, it is a measure of the ability of a material, or when we manufacture an article, how much suddenly applied load it can withstand without failure. It may also be defined as the threshold of force per unit area before the material undergoes fracture. Impact resistance is a complex function of geometry. That is, these are the parameters on which the impact resistance depends. That is the geometry, environment. By environment, we mean thermal and chemical. Material properties such as molecular structure, molecular weight distribution, chain length, what is the packing, what is the tacticity. We have already discussed the packing and tacticity in the classification part. Alignment and bonding forces. Certain parameters we have already discussed in the classification part. Now, the near instantaneous implementation of load, that is when we suddenly apply load to a material, it absorbs energy. When the amount of energy exceeds that which can accommodate, so far as it can accommodate that energy that is being supplied, the material will not experience the fracture. But when the amount of energy exceeds that which it can accommodate, the material will experience fracture, tear, or damage. This is what do we mean by impact resistance. Now, how do this tensile strength and impact resistance and melt flow viscosity? I'll be discussing melt flow viscosity in the upcoming slide. How do tensile strength, impact resistance? They vary with DOP. As we can see in this graph, tensile strength and impact resistance, they increase with increase in degree of polymerization up to a point after which slow increases there. In this graph, we have on the y-axis the property, that is what property we are discussing with respect to degree of polymerization. Here I'm taking up tensile strength and impact resistance. As we can see, they both increase with increase on degree of polymerization. The strength of the polymer rises with increase in molecular weight and reaches a saturation level at some value of molecular weight, and hence value of degree of polymerization is directly related to molecular weight, obviously. When we have lower molecular weight, now to understand this, when the molecular weight is lower, the polymer chains are loosely bonded by weak van der Waals forces, and the chains can move easily, which is in turn responsible for the low strength. Whereas at higher molecular weights, the polymer chains become large and there is cross-linking amongst these chains. When there is cross-linking, obviously the motion of the chains is restricted. When the motions of the chains is restricted, they impart strength to the polymer. The higher degree of entanglement, that is, they form a cross links, they get entangled with each other. The higher degree of entanglement allows the material to be pulled further before the chains break. So when the molecular weight is higher, there is cross linking and it provides strength to the polymer. So tensile strength and impact resistance, they increase with increase in DOP up to a point after which slow increases there. That is, after saturation, there is a negligible increase. And a high molecular weight and narrow molecular weight distribution enhances the impact resistance of the material, obviously. A greater degree of entanglement means that in order to rupture, obviously, more polymer bonds need to be broken. More polymer bond needs to be broken means that the polymer can absorb more energy before failing. So the impact resistance increasing. The more energy it is absorbing, more is the impact resistance. Now, what do we mean by melt viscosity of a polymer? The melt viscosity of a polymer at a given temperature is a measure of the rate at which chains can move relative to each other. As we can say, how chain flexibility is there, how much chains can skid over each other, how they can move relative to each other. This will be controlled by the ease of rotation about the backbone bonds. That is, how the backbone bonds, that is the main chain, backbone chain of the polymer, how much flexible is the backbone chain. That is, we discussed the chain flexibility of the backbone chain and how much is the degree of entanglement. Melt flow viscosity, as you can see from this green line, melt flow viscosity initially increases slowly, then rapidly after the polymer has attained a certain degree of polymerization. There's a slow increase and then the rapid increase. A high molecular weight increases the viscosity of the material, making it harder to process the material using conventional method, because high molecular weight increases the viscosity and it becomes difficult to process the material. The longer are the chains, the harder it is to get them to flow because they are more entangled now. They are more tangled now. So this green line clearly indicates that there is slow increase initially, and then after it has attained a certain DOP and a certain molecular weight, this suddenly increases. Thank you so much. So here we end with the lecture on polymer series. Thank you so much.